In the name of God, it's my pleasure to present to you our new article titled Reinforced Restoration of a Smart Distribution System Utilizing Transactive Flexibility of Prosumers at the 12th International Smart Grid Conference. I'm sincerely grateful for your attention to our presentation. Considering the customer's need for stable electrical energy with minimum interruption, the use of solutions that maintain the economic and reliability aspects of the distribution system has attracted the attention of many experts. One of the proposed solutions in this field is the using a smart energy distribution network. When a fault occurs in the network, the smart energy distribution network is able to detect the fault's location, isolate the fault, and restore service to other customers in the shortest possible time. In smart distribution networks, this process is known as the FLEST process, which aims to improve reliability indices such as SAIFI, SAIDI, and so on, as well as to increase the social welfare of customers. Increasing the penetration of variable renewable energy sources such as wind and solar has influenced the distribution network level and has many benefits for their owners. The participation of such resources, while considering their flexibility, can improve the restoration process of interrupted customers due to network limitations. A general classification carried out in previous studies on restoration and self-healing in the smart energy network is mostly divided into four categories: the reconfiguration of distribution networks, demand response, distributed energy resources, and transactive energy systems. In recent years, many researchers have paid attention to the concept of transactive energy as one of such emerging concepts in power systems. In the field of distribution network reconfiguration regarding restoration process, most studies have focused on the placement of all types of switches, including manual and automatic, as well as fault indicators. Articles 6 through 10 and 19 of this article's references address the placement of automated switches, whereas reference number 9 addresses the placement of both automatic and manual switches, and references 10 to 12 propose different models regarding the placement of fault indicators. In this article, references related to the usage of responsive loads have been examined. These references show how various demand response programs, including critical peak pricing, interruptible, curtailable, and emergency demand response programs, have been applied. References 13 to 16 and reference number 23 have evaluated these programs and their modeling. In the field of utilizing distributed energy resources to improve the restoration of the distribution network, most studies reviewed in this article have used electric vehicles that can be connected to the network and energy storage system. In modeling such resources, various parameters such as their availability, energy level, and the possibility of their participation in the process of self-healing and restoration of the distribution network have been considered. References 17 to 20 have examined this category. As mentioned in slide number 4, the fourth and last category refers to the concept of transactive energy and its applications in the energy distribution network. Transactive energy can be used, a new concept, to improve the restoration of interrupted customers in the distribution network by implementing local energy markets and using the flexibility of distributed energy resources. References 21 and 22 have examined the category of flexibility, and references 23 and 24 have examined the category of energy markets with the help of the concept of transactive energy. In the reviewed articles, various optimization methods such as classical methods and meta-heuristic methods have been performed in these four categories in order to minimize network costs. including customer interruption costs and other costs, such as installation of network automation equipment and the cost of using distributed energy resources. The modeling and methodology suggested in this article can be expressed in three sections. The first section of the model shows the prosumer solar cells flexibility in the backup feeder and downstream of the faulted zone. In the second part, the technical constraints of the network, such as voltage and current constraints, are discussed. And in the last part, according to the selected strategy and amount of flexibility determined during the optimization process, the objective function is calculated to reduce the network cost and improve reliability indices. In the first part of modeling, since the network's operation period is assumed to be 3 hours, the parameters of solar cells, such as the amount of radiance of the sun, have been used only in 3 hours, from 12 to 14. Although to obtain the value of solar cells flexibility contribution, a flexibility criterion has been applied in a normalized form. The technical constraints considered in this article are maintaining the radial structure of the network and not creating a loop, the limitation of the voltage magnitude of the buses, and the thermal limit of the lines. That the second and third limitations are investigated in the form of 10 modified load flow equations based on the selected strategy. In the last part of the modeling, the objective function and the reliability indices are calculated according to the two previous parts, with and without using the flexibility of solar cells. The objective function considered in this problem consists of two parts, including the total customer interruption cost and the total cost of purchasing power from prosumers. These costs must be minimized from the DSO viewpoint. Regarding the calculation of reliability indices in this article, four indices including the System Average Interruption Duration Index (SAIDI), the System Average Interruption Frequency Index (SAIFI), the Customer Average Interruption Duration Index (CAIDI), and the System Average Availability Index (ASI) have been calculated in two modes, without and with using the flexibility of solar cells. The proposed method has been implemented on two feeders of the fourth bus of the Roy-Billington test system (RBTS4) according to the figure. This network consists of two 11 kV feeders including 14 load points with a total of 2,180 customers and the use of isolation switches and maneuvering switches with 100% reliability, which play an important role in choosing a better restoration strategy. Also, on the right side, we can see the amount of load in each load point during the restoration process. According to this figure, the amount of load has increased significantly in the third hour. After modeling and implementing the proposed method, the results obtained from the implementation of the program are shown in the next three slides. In the left figure, the value of SAIDI index is shown for each load point. According to this figure and according to the characteristics of the studied network, the SAIDI index for load point 2, 10, 11, 12, 13 and 14 is reduced with the help of flexibility of the solar cells downstream of the faulted areas and the backup feeder. In the right table, the value of network cost and reliability indices are shown in two cases, with and without the use of solar cells. According to this table, the use of the flexibility of solar cells reduces the cost of customer interruption and also improves the reliability indices. The SAIDI index has decreased from 1.052 hours per customer per year to 0.888. The SIFI index, which is a customer-oriented index, is guaranteed to be stable in both cases since it is not related to the interruption duration. This slide shows an example of a fault in one of the network equipment. If it's assumed that the fault occurs on line number 13 in the network, according to the table, in the case of using the basic mode of the network in the first hour due to the low load of the customers, the first optimal strategy is selected and the customers of load points 10 to 14 are restored. In the second hour, due to a slight increase in load, the second strategy was chosen and only load points 13 and 14 were restored. And in the last hour, due to a significant increase in load and the congestion of line number 1, the backup feeder was not able to supply the needs of the load points in feeder number 2 and none of them are not restored. In the second mode and using the flexibility of solar cells, the restoration strategy was the same every 3 hours, but the load points that were restored in each hour were different. In the right graph, the amount of the flexibility index is shown for a fault on line 13, whereas it is clear in the figure the majority of participation was in the third hour. In the last slide of the results section, the amount of energy not supplied (ENS) by the system is shown in two modes. According to this bar chart, the amount of ENS in the mode of using the flexibility of solar cells compared to the base mode of the network has reduced from 7,784 kilowatts to 6,728 kilowatts. In conclusion, it's worth saying that the flexibility use of solar cells in smart energy distribution networks minimize line congestion by selecting the appropriate strategy, and this participation lowers the cost incurred on the network and improves network reliability indices. Additionally, it improves customer social welfare and lessens the amount of ENS. Thank you for your attention to this presentation.